some people start anyway. Okay. So we can project several vectors on different bases, which would correspond them to different coordinate system. Okay. So once we know these, the basis and the coordinate system, we learn all of these two elements because we want to conduct a linear transformation. So we want to transform a data, a matrix, a representation, a vector, a solution. So actually this is the most tricky, relevant, important for all of us. Often the solution of a system, they look better or they are represented in a more elegant way in a different basis. And for this reason, what we are going to see, what we are going to do this semester, the rest of the semester a lot, is the following. We are going to have a specific matrix which represents, let's say, an array of numbers, okay? And then we're going to have also vectors in this domain. And this is, let's call this one basis 1. Then we're going to have another domain, let me call it a domain, and this domain will be represented, instead of the matrix A, it would be a matrix D, okay? And instead of this vector X, we're going to have a vector Y. So, and we call this one basis 2. So far, we have covered in the previous chapters of the textbook, we know how different bases could be, how the same vector can be projected into different bases corresponding to different coordinate systems, okay? And now we come here and we're going to have one domain which can be represented according to basis 1, and another domain which will be represented by basis 2, and we have matrix A, vector X, matrix B, vector Y. Now, most of the time, let's say almost all the time, the basis 1 is going to be the standard basis, okay? What we mean with standard basis is the Cartesian coordinate system, okay? If it is two-dimensional space or three-dimensional space, let's call it the standard basis, which is composed of orthogonal coordinate system, where they are non-interfering, which means that they are also orthonormal, because the inner product between the bases is going to be equal to 0. Simply stated, we can say that the standard basis is the x-axis or y-axis, right? We might use to this representation, and the z-axis. Now, we could have four-dimensional space. This would be 1 with 3 zeros, 0, 1, 2 zeros, 2 zeros, 1, 0, etc. But let's call this one XYZ standard basis. The new basis that we're going to have, which is going to be the basis 2, most of the time, in a couple of sessions, or at least after one session that we're going to cover together on linear algebra, we're going to see that this best basis is going to be composed of the eigenvectors. Okay. So the eigenvectors of a matrix, they can be used. The eigenvectors of A can be used as a basis of the new domain, and the problem can be represented in a more elegant way. Okay. And now, what is essential for us is that we should be able to transform using linear transformations. Let me call this T and T inverse. Okay. So traditionally, if we can move from A to D using a linear transformation, this means that the linear transformation T, I could represent this one also as a matrix, times matrix A, this would be equal to matrix D, okay? And similarly, the same linear transformation can be applied on a vector X, okay, times a vector X, this would be equal to a vector Y. Now, we're changing the representation, what remains the same is the solution. Okay, so everything, and we're going to cover enough examples regarding this, and we'll try to make obvious as much as possible, and also easy. Now, in the last 30 seconds of this introduction, I just want to say also that this D, we prefer to have this matrix D as a diagonal matrix. Okay, so instead of having a matrix where we have off diagonal terms, which may be equivalent to having a system where we have coupling between different, let's say, different orthogonal directions. We want to transfer the whole problem into a diagonal matrix, which can help to do the diagonalization. So this keyword, you can write it down and remember, because in a couple of sessions we're going to work a lot on this one, and we should. So we're going to talk about the diagonalization, because diagonalization, it helps a lot into doing decoupling. So we might have a few variables which they are interdependent, so they affect each other, but it is always the best way to have these systems or variables independent of each other, solve them, because it might be easier. So with this small review of what we're going to see next, we can start covering a couple of theorems or a couple of rules that will help us to understand the elegant mathematical apparatus, which is the basis for these beautiful things that we're going to cover very soon. So we're going to talk about the linear transformations, and linear transformations, they are defined as any t, which is defined from a vector space V into another vector space W, and these vector spaces, we should have also the zero should be in this vector space V. So we can see that often we like to have the zero in the vector spaces that we are discussing. And one of the major reasons for this, that I'm sure you might be expecting this, is that we want to have both the linear transformation T, which can help us to go from one domain to another, and we want also to have T inverse, which will bring us from the second domain to the first one. But once we have these, I think we remember when we talked about the spaces and the subspaces, just as a reminder, I want to say that for a set to be a subspace of a larger domain, we like to have the minus vectors. So if we had X, we like also to have the minus X in the same space, because this would be equal to 0 vector. And in order to have this, we preferred, it was very essential for a space to be a subspace of a larger one if it had a 0. And this was one of the smartest and intuitive approaches to check whether something is a subspace of another space by checking whether the 0 is there. Now, the moment that we want the linear transformations and inverse linear transformations, which inverse linear transformations, they can be defined like this. Imagine for a moment, TA would be equal to T. We can multiply both sides with T inverse, right? And then we will get that A itself would be equal to T inverse times D, which means that we can come backwards like this. So linear transformations, they are transformations from V to W for 0 in V, and we want also T in the matrix notation, because times the 0 vector, this should be 0 in the subspace as an element of the space W. Now, we want this because the 0 vector in the V space, it could be R cubed. The 0 in the W space, it can be R4, right? So these 0 vectors, just for, I can even just simply say that this 0 can be 3 by 1, okay? This is just an example, okay? And this 0 here this would be 5 by 1, depending on what the linear transformation is doing. This is just little hints or reminders for you to think about where we are going. Now, let's mention the first theorem. So, a linear transformation T, which is defined from Rn to Rn, this is the linear transformation, and we can say, let E1, En be a standard basis of Rn, And let A be a matrix composed of the T of E1, T of E2, and T of En. Now, all of these T's, let's not forget, these are the linear transformations. And then, now, when we say that these are E1, E2, and E3, and we're calling it the standard basis, I want to remind all of us that these are E1, E2, and E3. So what we name as the orthogonal Cartesian coordinate system, this is the standard basis, okay? We know that a basis can also look like this, right? 1 minus 2, 2, 1, 3, minus 7, and 9 minus 1, minus 3. This is also a basis for three-dimensional space, but this is the standard one. This is E1, E2, E3, okay? So just as, and then we can say that T times a vector x, it can be represented by AX, okay? So in principle, what we are really saying, we're kind of offering the introduction that any linear transformation, it can be in principle equal to a matrix times a vector. So LPs, they can be represented by matrices, and this is the reason that these linear transformations, you might see me denoting them as a double-headed arrow. You don't see this much in the textbooks, but I might use this because it awakens the idea that the matrix can do anything. Let's assume for a moment, let's see an example, where linear transformation T is one that can transform from R3 to R3, such as the linear transformation affecting x, y, and z. This would be equal to x plus y plus z, x minus y, and x plus 2y minus 3z. Now, let's see. So this is a linear transformation. In order, so now the big question is the following. So let's try to pick up where we want to go, or what do we mean? We want, so we are given this. The big question is this. This is what we have to find, okay? What is the matrix which represents the transformation from here to here, or from here to here? So this is the question. How do we find it? We have, because we have to find this one in standard basis. Okay, this is another keyword. So this is what we should keep in mind. We should try to determine what is this A in standard basis. How do we find it? We find it by applying, instead of x, y, z, we have to apply E1, E2, and E3, which is 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. So let's do this. Let's do the T times E1, which is the linear transformation times 1, 0, 0. And this would be equal to, if we substitute here 1, 0, 0, you can help me here, we'll get, so x is 1, y is 0, z is 0. So for x1, so let's do it like this, 1 plus 0 plus 0. Then we have 1 minus 0, 1 minus 0. Then we have 1, 1 plus 2 times 0 minus 3 times 0. Okay? So this is how we apply the first, standard basis axis. Then here we get 1, 1, 1. Okay? Then we have to find what is the second column of the matrix A. Sorry, this is not good. This is 0, 1, 0, and this would be equal. Let's try 0, 1, 0. This is going to be 1 minus 1, 2. 1 minus 1, 2. And t 0, 0, 1. So what are you doing now? You can always go back, look at this definition, and see what we are going to obtain. 0, 0, 1. We have these two are 0. We have a 1 here, which is 1. This is 0. We have the only non-zero term is minus 3 here. It's minus 3. Okay, with these values, then it looks like the matrix, the big question which was here, the matrix which is going to conduct this transformation from here to here, with this result, is going to be the following: 1, 1, 1, 1, 1, 1, 1 minus 1, 2, 1, 0, 3. Okay, so this is the yes. Say it again.
Minus 3.
Yes, that's true. It's minus 3. Thank you for correcting this. Okay, so this is the now regarding these, a good example are the rotation operators. Now, for a moment, let's think about the rotation operators. And before we go into the rotation operators, let's just think for a moment. I mean, what is a matrix? Let me ask you the following. Now, this became a little messy situation, but let's assume the vector 1, 1, 0. What would be the answer here? Can somebody in the class help me here? So what is this? I'm just applying this matrix A on this vector. We have 1, 1, this is 2, this is 0, this is 3, 3. Would you agree that this is the answer? Now, I want to ask you, what is the magnitude of this vector? 1, 1, 0. What is the magnitude here? You can raise your hand. I can see this on the comment section. Okay. Yes, Lawrence, you gave that's correct. But what I mean with the magnitude, I mean the length of the vector. The magnitude.
Square root of 2.
Square root 2. That's true. So here we're talking about square root of 2. What is the magnitude here? This is
square root of 13.
Square root of 13.
That's correct. Square root of 13. So in principle, what a matrix does to a vector, it rotates it and it changes the magnitude. So you rotate it and you expand the vector or you contract it. Okay, this is what a matrix is doing. For sure, this vector is being rotated because this is not in the same direction. 1, 1, 0 is not in the same direction. 2, 0, 3, right? So that's good. We see the rotation. We see also the magnitude change. But just for the moment, let's think about only for the rotation operator, which means that we are keeping the magnitude. We have this vector. We just want to rotate it, okay? We don't want it to rotate it and make it a longer vector. So these rotation operators, let's assume we want to rotate a vector counterclockwise in the opposite direction with the arms of a clock, counterclockwise by an angle theta, okay? Now, so how can we rotate a vector by an angle theta? Well, so we want to find the representation. So in principle, how can we find this matrix A? So the question is the same. A is what? Okay, the same question we just asked before a moment. Okay, and how can we find this matrix A? Well, what we need to do is that we need to rotate the E1. So it's two-dimensional space, right? Let's do it on the board. Let's think that we are dealing in R square, and the basis for R square is E1 and E2, right? This is, we can spell the R square using these two. What is E1? E1 is 1, 0. We can write it like this, and E2 is 0, 1, okay? So what happens to this vector here? What happens to this vector here if we rotate this one by an angle theta? This will be projected onto here, right? And here. Okay? So then this one, we say that this linear transformation T, which was applied on 0, 1, 0, this is going to be equal to, so what is the x-axis here? X-axis was 1, the y-axis was 0. What about now? Now, this would be cosine theta and sine theta. Okay, so this is the linear transformation here. Then, what is the linear transformation? Or how will the vector 0, 1 change given this, this definition? This vector here, which is 0, 1, is going to be rotated here, and the projection of this one is going to be this vector in the negative x-axis.
Minus cosine.
Say it again?
Minus cosine theta.
Let's see. You mean this one, right? Is it minus cosine? Shiko, për të bërë këto lloj shembush, mendoni një këmbë të ngushtë, sepse po të bëni këmbë të ngushtë ju ndihmon më shumë. So think for a moment. This is theta, right? So this longer side, kjo më e gjata, kjo është cosinus. And we're doing this is cosine, right? So then what is this? This should be sine. So kjo është brinja e shkurtër, dakor? Would you agree here?
Yes.
Okay, so it looks like the projection of this new vector is going to be minus sine. For the x-axis, this is minus sine theta, because apparently it looks like cosine is the larger side, and here the y-axis it was 1. The y-axis it was 1. When we rotated it, the y-domain is going to be equal to cosine theta. Cosine theta, okay? So this is the linear transformation that we wanted. Now, this means that the matrix A, which is going to represent correctly this transformation, will be the following. Matrix A is going to be equal to cosine theta, sine theta, minus sine theta, cosine theta. Now, we can ask each other, what is the determinant of this matrix? What is the determinant of A?
Cosine square plus sine square.
It's 1.
It's 1, right? So determinant here is equal to cosine square plus sine square, and this is equal to 1. These matrices are called unimodular, okay? So the matrices that are unimodular, they have determinant equal to 1, and they are very good at preserving certain quantities, okay? Or they are very good at preserving certain properties of vectors. So here you can, they have many properties. You can read a lot about these. You can study together a lot of the properties that they might have. Now, let's think for a moment. So let's assume if theta is equal to pi over 4, what do we get here? Or this is pi over 2, okay, or pi over 2. So what is A? This would be straightforward, actually. So A, if the angle is pi over 2, what is cosine of pi over 2?
0, -1, 1, 0.
That's true. So this is the rotation by pi over 2. What about an angle of by pi over 4? Pi over 4, this would be 1 over square root of 2 minus 1 over square root of 2, similar, right? Now, we're talking about, this was pi over 2, this is pi over 4, you can check it. We talked about the unimodular matrices, which have this beautiful property, and for the moment, it is very good to think about this specific operation. And the concepts that we're going to see very soon will be the following. I'm just writing them down, so when we come up to those, you say, okay, we saw this, we talked about this one before. I want to also to remind about something that sometimes, not sometimes, often we can multiply a vector by a matrix. We learned what it does. It rotates and changes the dimension. But there is also an equivalence sometimes where this would be equal to a constant number times a vector, okay? So sometimes we don't change the direction of the vector at all. We just want to have, we want to separate or we want to express a single linear transformation which has rotation and the magnitude change. We want to decompose it into two different linear transformations. So imagine for a moment that you want to express the rotation by one matrix and the change of the length or of the magnitude by another matrix, okay? Such as they are non-interfering. So keep this in mind. Let's move to the next topic. Okay. So about the different linear transformations, we can define identity LT. So linear transformations, let's denote them as LT, or sometimes we might even see them as T, okay, like transformation. Now, we can define identity LT. What is an identity LT? It is such as any linear transformation T on a vector V. This is going to be equal to V. Now we can write this also this way. Okay? It is not going to be a mistake. Just that if you forget which was the correct notation, don't worry too much. We want to, because you can write it either way. Don't worry. We can even write it like this. The matrix which is going to represent this linear transformation, you can do it like this: A times V. This is equal to V. And by now, you even know that this matrix, which has no change on the vector V, most of the time, or let's say all of the time, is going to be the identity matrix. And the identity matrix, you know, it's zero every element, with the exception of the diagonal terms, which are going to be 1. Now, this is the identity linear transformation. We have also the zero transformation, which means that 0 LT, which means that every vector, we can project it to the 0, okay? So the whole domain, we just throw it into the, consider it like a vortex point, which absorbs everything. So zero linear transformation would be 1, where T times V, any vector V, would be equal to a 0 vector. So it's somewhat like, so when could this happen? This could happen whenever the A times X would be equal to 0. And where have we seen this before? What could the X be?
Inverse.
There should be only one solution.
Null space.
Null space. This is a better answer, okay? So it's going to be the null space, and we know that null space it might have an infinite number of points. So the null space can be a surface area, or let's say a plane which expands, but it can be the surface of a sphere, whatever. Now you are applying a linear transformation here, okay, and everything goes into the 0. This is it. And this is really the projection of the null space of a matrix into the 0. We have seen this a lot. It is possible. Yeah, and this would be the linear transform. Sorry, the 0 LT. Yeah. Now we can have a combination or composition of linear transformations. We don't have only one, but we can have, what we can do is that we can pick up a vector so we can define this one as combination and composition of linear transformations. Now, if T is defined from V to W, from one space to another, and another linear transformation S, which is defined from W to U, then ST, now this is a single linear transformation, is a linear transformation 2, is, let me call it, is a linear transformation 2. Okay, so now you can think about this. V can be R cubed, this can be R4, this can be R4, this can be R6. So it is possible for us to transform a vector initially by T and then by S. Okay, and so in this case we would say that so this is one LT, this is the other LT, and what we are saying here is the following. So S times T times the vector V. So what is happening here, we are initially calculating this, and this would be equal to S times a vector W, which would be just representing, and this would be equal to U. Yeah. And now the thing is that we can also say that this was a linear transformation, but this linear transformation, we know that we can represent this by a matrix AT, okay? The matrix covering for this transformation times V, and this S, it can also be represented by a matrix which we can call this one AS, okay? And this then would be equal to AS times W, and this then would be equal to U, which in principle, this means that matrix AS times matrix AT, so times the vector V, this would be equal to a vector U. Okay, so in principle, we're doing matrix multiplication. Another important thing that we can say about the linear transformations is the inverse linear transformations. Or actually, what I might add here is that the combination of, or the composition of linear transformations, what could be very interesting, now forget about this one, so this is just a general definition or the general introduction of how transformation can be combined or composed together. Imagine for a moment that we could represent the matrix A by a rotation matrix, okay, R, and by another matrix which does the extends the length or compresses it. So let me call this one length modifying matrix. Okay, so this is something which is which we can think as a vector. We can rotate it first by a specific angle. And how can we conduct this from here to here? This is equal to vector x0. This is, what is this second vector? This is vector which is equal to rotation matrix times x0. And then we can get, we can apply to this vector another operator L, and this would be equal to L times r times x0, which will be then equal to a times x0. Okay, so this is one way that you can think about the decomposition of a single matrix A into several other compositions, and each one of them is doing only one single change at a time. Okay, what we are going to see a lot, and I want you to keep note from now, so that when we come back to this chapter, you'll say, okay, we saw this again. A very common transformation, or the best possible linear combination of several transformations, is the following: is R1 L R2, which in principle this means that the effect conducted by a single matrix can be done by rotating a vector, changing the dimension, and rotating it again. Okay, but this is how this can become useful in the future chapters. Now let's talk about the inverse linear transformation. So we have identity linear transformation, we have also inverse. And since we know matrices and inverse matrices, we all know very well how this could play into our discussion. Inverse LT, let's call it like this. The inverse LT, it is defined, so if P is defined from V to W, then the P inverse is defined from W to V. Okay, and then we can also say that the P inverse times P on V, this is going to be equal to P inverse on a vector W, and this will be equal to V again, which means that this matrix, this linear transformation T, it can be represented by a matrix which is AT times the V, the vector on which it's being applied. This can be another vector T inverse, and in principle, this will be A of the T inverse times A of T times V. This is going to be equal to V, which means that this is the identity matrix, which also, from which we can also conclude that the A of the T inverse is in fact the A inverse. We can say that this looks like a little messy, but this is going to be equal to the inverse of AT. Okay, so they will be inverses of each other. Now, when it comes to the rotation matrices, we just looked at the seconds, yeah. So we had the following. We had A theta. What was A theta? Which was the rotation matrix? It was cosine theta, sine theta, and then you told me that this was the minus sine theta when we had the geometric representation, and this is again cosine theta. Okay, this is one linear transformation. Then, without going into too much detail, let's try to define another transformation which brings the vector back. So we had it 0, 1, we rotated by angle theta, we want to bring it back. Now, this bringing it back, we want to define this one as A minus theta, okay? So what would be A minus theta? This would mean the rotation by a different angle. This would be cosine minus theta, right? Cosine minus theta, sine minus theta, minus sine minus theta, and cosine minus theta, okay? We have no doubt this is true. So this is the inverse rotational matrix. But for someone that memorizes very little or almost nothing, we want to have a look actually. What is cosine minus theta? So if we have a narrow angle, so this is angle theta, what is the cosine of this angle? How is it related with cosine minus theta? So this is theta, this is minus theta. How are the cosines related?
Equal.
Thank you. They're equal. So it is obvious, right? Because the projections of these two, they are right here. Sorry, this is back more. So we said that these two are equal. Now, since we are here at the board, what is the sign of this theta? It's right here. It's this vector here. What is the sign of this minus theta? So here we have the angle theta, here we have the minus theta. So what is the sign here?
Minus.
Is the negative one. That's correct. Okay. That is the negative. So here simply we can say that this is cosine theta, this is minus sine theta, and here we have sine theta, cosine theta. So here we have two linear transformations which we expect them to be inverses of each other. So at this stage, what we could do, we can simply multiply matrix A with matrix B and see what we get. Now, to make it simpler, I can multiply it here. This is cosine minus sine, sine, cosine. Okay, I just multiply the B right here. The answer here would be cosine squared plus sine squared, this is 1. Cosine sine minus sine cosine 0. Sine cosine minus sine cosine 0. Sine, let's do carefully this one. This row with this column is equal to what? Sine squared plus cosine squared is 1 again. So it looks like really the rotation matrix times its inverse rotation matrix gives the identity matrix. Okay. Now, if you like, we can have a short break and we'll continue again.